Alright, let's get started. So, welcome everyone to another lecture in our ID 5130 Parallel Scientific Computing course. So, in the last lecture, we finished discussion on OpenMP programming. Right, we looked at all the relevant function calls, as well as the compiler directives and the OpenMP sentinels for compilation, as well as looked at the scope of the variables and the loop directives, scheduling, critical directives, and so on. Okay. Now in today's lecture, we're going to start a new chapter, that is the chapter 3, which is essentially numerical methods using OpenMP. Okay, we will see how to essentially apply the concepts that you have learned to some of the numerical methods problems, so that they kind of give some kind of confidence in terms of going ahead with your own numerical methods that you work with in your research or in your projects. Okay, all right. So I'm going to look at few basic numerical methods today. First one is first couple of ones are very simple. The first one is basically matrix addition. So these are actually very straightforward. Another one is matrix multiplication, and thereafter we will look at explicit finite differences, explicit spatial derivatives, or finite differences. Okay, as well as the final one is known as the implicit finite differences. All right, let's get started with addition of matrices. So the first one is addition of matrices. So this, as you guess, is very straightforward. So when you looked at how to add vectors, the same thing can be applied for addition of matrices. So essentially, if you have, let's say, two square matrices, A of size n by n and B of size n by n, now we would add, when I say addition, we would add element by element, right? We would add element by element, and then each of these elements will be, the sum will be stored in the final matrix C, which is also a square matrix n by n. Okay, so the one of the earliest examples, the programming codes that were provided, kind of already has the addition of matrices in both C and Fortran, so that you can make use of to write it in parallel. So if I look at the loops, for example, if we denote I for a row and j for a column, right, we can write the addition of matrices, and then we have three matrices basically, that is A, B, C. Each of them are of size n by n. Okay, now we can write the matrix addition using two for loops, that is basically a loop over a row as well as a loop over columns, right? If you have a first for loop is basically loop over the rows, as well as the second for loop is j equals 0, j less than n, j plus plus, right? So this is the loop over the columns. Then you can write C of ij, that is the summation matrix, equal to A of ij plus B of ij, right? So that is your regular serial for loops, right, to add elements of the matrices and then store them in the final summation matrix. Now what about now if you want to parallelize this? Are there any loop dependencies, or are there any loop carry dependencies or data dependencies when you try to parallelize them? Let's say we want to use our natural parallelization, that is basically parallel for. Okay, we would like to use this either for the first one or for the second one. Can we do that? Well, if you do it for both of them, it would become basically nested for, right? Of course, you can do either of them, right? You can even include parallel for only for the top one or for the bottom one, or you could include for both of them, right? Only thing is that you have to set nested equal to true if you are doing for both, because there are no essentially data dependencies or loop carry dependencies, because each ij would uniquely belong to each of the threads. Okay, so as a result you can do all these three kinds of parallelization. And what about how would you declare the the pragma here? So essentially you would write it as hash pragma OpenMP. Let's say if I'm only parallelizing the top for loop, so I would write it as OpenMP parallel for. Okay, we would write hash pragma OMP parallel for. So that is basically parallelizing only the first for loop. And then how do we define ij and abc? So we can say default none, so that we define essentially each of the variables that are there. And then we can say what will be the scope for matrices ABC. ABC can be shared, right? Because anyway there is no dependencies on them, because part of them can be updated simultaneously using the different I and j that belong to the threads. And then what about ij? Ij should be shared as well or private? Ij should be private, right? Either I or j. So these are basically private. So once you do that, you could have your own you could have your for loop that is for I equal to 0, I less than n, I plus plus, and then you have the other for loops as well. So you have the next for loop is for j equal to 0, j less than n, j plus plus, and then you have this c of ij, right? Now in this case, which of these for loops will be parallelized? Will both of them will be parallelized, or only the top one? Only the top one, right? Okay. If you want the other one also to be parallelized, then you have to have another parallel for, and then nested equal to true, and so on. Okay, so that is quite simple for the matrix addition. Now let us move on to matrix multiplication. Matrix multiplication is slightly little more complicated. So matrix multiplication, so you have two matrices. Again, we have two square matrices, A of size n by n and B of size n by n. We have to multiply them and then calculate what is the resulting multiplication matrix C of n by n. Okay, how would you go about the matrix multiplication? This is has been done many times by you. So you have matrix A and then you have matrix B, right? So to calculate the final matrix C, you calculate the final value here, you have to multiply this row with this column, right? Essentially you would multiply I equals 1 with j equals 1, and then you multiply each of these elements, right? Right, with I1 with j1 and so on accordingly, and sum all of them, and then that's going to be your resulting element here, right? Accordingly you would also fill up all other elements in this C matrix by multiplying, by choosing separate different columns and different rows, and then you would fill up those values here. Okay, so essentially you have one row multiplying one column, right, element wise, and then sum all of them, right? That's what the algorithm is, right? You essentially have, okay, so this is basically a symbol, okay, not zero. All right, so to put it simply in a in an algorithm, what we have is you have to loop over all the elements of I as well as j, and then for every I you have to for all j you have to multiply for one j all the I. Okay, so essentially what you have is you basically have the one for loop that loops over all the rows of the matrix A. Okay, that means you have for I equal to 0, I less than n, I plus plus, right? And then you have for j equal to 0, j less than n, j plus plus. You have the for every row you have all the column data, right? And then all the columns is j equal to 0, j equal to n, j plus plus. Then what you need is you would need another for loop. That for loop will basically multiply a element a11 with b11 and then sum it, right? And then similarly you have a12 and then b21 multiply and make the summation, right? You need this thing a13, b31 and so on all the way to a1n, bn1, right? Now that summation basically would give you what is c11. Okay, so you would need another for loop, that is your innermost for loop. Let's call it for k equal to 0, k less than n, k plus plus. Okay, so in the innermost for loop, and then you have essentially, I would write it here although the indentation doesn't allow for it, So Cij, basically you are having updating the particular row and the particular column in the final C matrix as Cij plus A of ik, and the k is acts as the pseudo column here, and then multiply that with B of kj. Here k acts as the pseudo row. Okay, so this is pseudo column, this is pseudo row, and then accordingly we have this final implementation for the matrix multiplication. Okay, so essentially we have 3 for loops. Okay, and then now what about parallelizing this thing? Now can we, is there a loop carry dependency or a data dependency? Let's say if you try to parallelize the first for loop, let's say if you want to parallelize the first for loop, is there a loop carry dependency? So it means you're going to decompose rows of A, you're going to give few rows to thread 0, another few rows to thread 1, and so on, few more rows to thread 3 tn, and so on. Okay, so basically you have that belongs to t0, this belongs to t1, t2, and so on, right? Now as you can see, all you have is ij, ik, kj, and then k is not parallelized anyway. So you have basically I and j, which are unique, and when every thread gets it. So if you can share A, B, C, all the matrices, and I and j are private, then there is no loop carry dependency or data dependency if you try to parallelize with the first for loop, right? That means if I were to write my program, right, as like this, that means what I would write is, I say hash pragma OpenMP, right, and you say parallel. I can say, let's say this is basically parallel for, right? So I basically have 2 pragmas, right, which are basically so I just have parallel, and then I say default none, and we have shared is basically A, B, C, as well as the size of the matrix n is also shared, right, which I missed in the previous case, right? N is also shared because n doesn't change. And then we have the private clause. Okay, private is basically for I, J, and K, right? That's what we have. Okay, so we have these 2. Now what about C of ij? C of ij is C of ij needs to be is basically adding these values. So C of ij needs to be initialized to a value of 0 before we actually go about the summation. Okay, so the first thing we have to do is we have to first initialize the C of ij to 0. So in this I would write another hash pragma OpenMP for. Okay, so we have for, and then I would say for I equal to 0, I less than n, I plus plus. Then we have for j equal to 0, j less than n, j plus plus. And then in this we would write our first initialize C of ij equal to 0.0. Okay, so that's what we would do. So that hash pragma for now ends. Okay, then we have essentially initialize the matrix C to 0.0. That means now we can go about adding them. Then we have one loop which we would like to parallelize the outermost for loop. So we have hash pragma OMP for, that is sufficient because we are already in the parallel block, right? So then I can say for I equal to 0, I less than n, I plus plus, right? And then we can say, so this is the loop that will be parallelized now. Okay, and then now I can say for j equal to 0, j less than n, j plus plus. Okay, and then we have for k equal to 0, k less than n, k plus plus. Then we can write, of course, C of ij plus equals, right? We can say A of ik star B of kj. Okay, so that would be fine. And then I would close this for loop, and then I would also close the hash pragma that we have opened here. Okay, so this is closed here. Okay, so far so good. Basically we are able to now parallelize the outermost for loop, right? Now, now of course you may think that, okay, shall we, because this hash pragma OpenMP for is independent from this hash pragma OpenMP for in some sense, although we would like to have the corresponding Cij to be initialized to 0 before it is updated, right? What we may be tempted to write, let's say, OpenMP pragma for no weight here, okay, but it is probably not a good idea to write it that way, because the assignment of threads to the particular Cij is not guaranteed to be the same between these two. Okay, so as a result, writing this no weight can cause issues. So let us not write no weight. That means all the threads will finish this, then only all the threads will do this. Okay, so these two are essentially sequential in that sense, but they are parallel when you come to each of the implementations, of course. Okay, that means we have now kind of parallelized using the outermost for loop. Now what about the parallelizing the second for loop, the second one that we have? That means, so let us say this is implementation A, okay. The implementation B would be parallelizing both the for loops. Okay, that means we again have, it appears from here that even ij, because both of them are, you know, kind of independent, there is no loop carry dependency. As a result, this can also be, both loops can be parallelized. So we have hash pragma OMP parallel, again we have, you know, default none, right, shade A, B, C as well as N, and then you have the private variables are your same as before. This is I, J, K, okay, and then you have hash pragma OMP for, right, and then you have the outermost for loop, that is for I equal to 0, I less than n, I plus plus. I mean, you can write the similar things for Fortran as well, which I haven't written here. And then you have another hash pragma, right, that is for the second for loop. That means you have to again switch on the nested parallelism here for j equal to 0, j less than n, j plus plus. So you have multiple threads forking here, right? Again, whatever the threads that have forked here will again try to fork more threads here, right? And then you have, of course, we have now missed the Cij part, so what we can do is we can initialize it here, Cij equals 0.0 before we go for the third loop, that is k equal to 0, k less than n, k plus plus, right? And then we have our implementation here, C of ij equal to, or essentially plus equal to, right? This is plus equal to a of ik star b of kj. Okay, that is kind of sufficient. So we close this this for loop for j, we close the for loop for I, then we close the hash pragma outermost for loop. Okay, so that way we can parallelize both the for loops for matrix multiplication. Now my question to you is, now what about the innermost for loop? Can we parallelize this k loop as well, just for the sake of it? Is it possible or is it not possible? Maybe you can think about it and see. Okay, all right. So, but unless the matrices are very large and the number of threads are also, you know, large, you don't really need to do two nested parallelism as such. Even just doing the outer one would be sufficient. Okay, as such. Okay. All right. So that kind of finishes the discussion on the matrix addition as well as the matrix multiplication. You know, how to parallelize them using OpenMP. Now let us look at a few things about spatial derivatives in general, and then see how can we go about you know, parallelizing them. So let us see how to first of all compute the finite differences or explicit spatial derivatives and implicit spatial derivatives from a numerical methods point of view, and thereafter we will see how to kind of you know, parallelize them. All right, so okay, so let us see the explicit finite differences. So that is 3 explicit finite differences. Okay, So essentially, if you're dealing with, let's say, a finite difference method or a finite volume method or any other method, you will kind of come across essentially a grid, that could be either just make it horizontal. Okay, so you will probably come across a grid that will have essentially several points. So let's say we consider a 1D grid like this. It will have let's say uniformly distributed points. If you were to call it as starting from 0, 1, 2, 3 all the way to n, then it has a length of L. So this is basically a 1D problem in which you have kind of discretized your domain using several points. Okay, yeah, essentially now you can also probably work with 2D problems, right? In 2D problems you have a grid that is either could be uniform or non-uniform, right? So we have a grid like this, and then you have several points not only in the x direction but also in the y direction. So this is pretty standard when you deal with, let's say, finite difference method or any other method. Okay, so and similarly you can also have a 3D kind of system, right, where you have points in the third direction as well. So basically you have x, y, and then using the right hand screw rule you have z as well. Okay, so then you would essentially end up with more points, and then you may have here probably have m elements in the x direction, n elements in the y direction, or you may have m n by p in the x, y, z directions as well. Okay, so those are the number of grid points that you may have. Now whenever you deal with, let's say, ordinary differential equations or partial differential equations, you end up with some kind of derivatives of functions, right? And these derivatives can be either first derivatives or second derivatives and so on. Okay, now the idea is, now that we have discretized the system, we have converted our continuous problem, right, into a discrete problem, right? That means whatever solution we obtain, we only obtain it at these discrete grid points. So we would not know what is the value in between. I mean, you could always use an interpolation and calculate what is the value in between, but that may not be accurate as such. Okay, so the continuous problem is converted to a discrete problem using this particular discretization. Then how will you express the derivatives of a function, okay, whose values are only known at discrete points, right? Then that is what basically is dealt by explicit, or basically finite differences, or spatial discretization, or spatial differentiation, or spatial derivatives. Now essentially what you would recall is you will use Taylor series expansion and try to express the function value in the neighborhood. Let's say if you call a particular value 2 as I, its neighbors would be I plus 1 would be 3 and I minus 1 would be 1. And then if you also assume that you have a uniformly spaced grid points, then and each of them kind of differ by a value of h or delta x, okay, where h is basically equal to L upon n. Okay, then you can represent these locations as the coordinate of 3 as xi plus 1 or x3. Similarly, you could have xi minus 1 and xi and so on, right? Then using Taylor series, you could write express the function value at xi plus 1 as f of xi, okay, plus you could write this as xi plus 1 minus xi times derivative of the function at xi, plus you could write this as xi plus 1 minus xi whole square by 2 factorial multiplied by double derivative of xi and so on, right? Now we already know that xi plus 1 minus xi is equal to the distance h. Then if I use a shorthand notation for f of function value at xi plus 1, if I write it as f I plus 1, simply write it as fi plus 1, then we have fi plus 1 equals fi plus you have h times f prime I plus h square by 2 factorial times f double prime of I, then we have h cube by 3 factorial times f triple prime of I and so on, right? Okay, so using Taylor series we have expanded this. Then we are interested in calculating the value of the derivative at that particular value at the particular location. So you can extract what is fi prime from here by rewriting this thing. That would be fi plus 1 minus fi divided by h, and then you have the remaining terms that are going to the left hand side would be minus h square by 2 factorial, but then you are dividing with h, so it will become, you know, essentially h by 2 f double prime I, and then minus and so on. Okay, so basically we have certain terms which will contain higher order derivatives, right, when compared to the derivative we are trying to evaluate. Okay, so that means we can write this in a simple way as fi prime equals fi plus 1 minus fi by h plus order of h. Okay, so essentially we say that these terms that contain the higher order terms, you know, fi double prime, fi triple prime, and so on, we will not consider them, rather we will be truncating them. Okay, and we are going to approximate our fi prime using fi plus 1 minus fi by h. Okay, and then we are going to say that this is the truncation error in representing this derivative at I using only these 2 point function values. Okay, that means this is basically a first order, because the h has a power of 1 here, the leading order is h to the power 1, so we can say that this kind of approximation is a first order accurate finite difference formula. Okay, so and also because fi prime only depends on fi plus 1 and fi, this is also known as a forward difference. Now similarly you can also write you know, for f xi minus 1 as simply as fi minus 1 in terms of express it about xi, that will be f of I minus h times f prime I plus h square by 2 factorial times f double prime I, and then minus h cube by 3 factorial f triple prime I, and so on. Okay, then we can write what is express what is fi prime using these two values, that is basically fi minus fi minus 1 divided by h plus order h. So this is also a first order accurate formula, right? The only thing is that now this is basically, if you want to calculate I, it depends on the function value set I and I minus 1. So this is more like a you know, the backward difference. Okay, because we are going in the values of I that are smaller than the I that we are trying to compute. Okay, so similarly by using, let's say, let's call this equation 2 and let's call this as equation 1, by subtracting equation 2 from 1, you can also write an equation for fi prime in terms of fi plus 1, fi minus 1, you know, with a distance of minus fi minus 1 by 2h. Okay, and then you would essentially end up with the other term gets cancelled, only the this term will remain. This will basically be h square by 2 factorial, or h square by 6, right, times fi triple prime, and so on. So basically this is known as a order h square truncation error, and this formula is known as a central difference formula, because it depends on fi prime depends on fi plus 1 and fi minus 1 in a symmetric way. Okay, now the truncation error, as you can see, is second order accurate, because h has, you know, an order, the leading term is order h square, so this is a second order accurate formula. Now what does this truncation error mean? This truncation error means that as you refine your h, as you take your h to be, as you half your h to be h half, you know, your truncation error would go down from truncation error here to truncation error will go down by 4 times, because the truncation error goes as h square. So if you make it half, it goes down by 1/4. If this scheme was first order, then if you just make the grid size to be half, your truncation error will only go down by 1/2. In addition, for example, if you had a scheme which was order h4 having truncation, that means if you had a fourth order accurate scheme, okay, then if you half your mesh, then your truncation error would go down by 1/16th, right? So that is kind of the power of the higher order accurate schemes, wherein the truncation error involved, which is the error involved when you try to compute the derivatives, goes smaller and smaller as you keep refining your mesh size. Okay, so essentially the higher order accurate schemes are nice. So by manipulating the, you know, the fi plus 1, fi minus 1, and by including other terms called fi plus 2, fi minus 2 and so on, you can come up with several higher order schemes. One such scheme is what I would list here. So you can approximate fi prime to a fourth order accurate scheme by using fi plus 2 minus 8 times fi minus 1 plus 8 times fi plus 1 minus fi minus 2 divided by 12 times h plus order to the power h4. Okay, so such higher order schemes, even higher order schemes, can be also derived by using the Taylor series expansion. Now these schemes are really nice because the truncation error would be smaller as you make your h smaller and smaller. But the problem with higher order schemes is that they require data. For example, fi prime requires data for I plus 2, I minus 1, I plus 1 and I minus 2. That means if you are at I, it requires I minus 1, I minus 2, I plus 1, I plus 2. That means if you happen to be on a boundary, okay, of your domain, then it not only requires data which is inside, which is fine, it would also require data which is outside the boundary. Okay, now these data is actually may not be available, right? Even for serial, we have not kind of started talking about parallel at all. So that means this data may not be available. As a result, you may have to come up with the one-sided formulae that we have discussed before, okay, to be used on the boundaries or near the boundaries, right? So that you would not need the data that is outside. Okay. Alright, similarly, just like we have derived the first derivative, you can also derive formula for the second derivative. Fi double prime would be equal to, if you work with the Taylor series expansion, you can show that this to be equal to minus 2 times fi plus fi minus 1 by h square plus order h square. Okay, so that's your basically d square f by dx square at x location xi. Okay. Now these are called explicit finite difference formulae, as you already understand, because to calculate the value of the derivative, you basically, all you have to do is basically use this explicit expression, right? Essentially you plug in the values of f at either I plus 1, I minus 1, I plus 2, depending on the stencil. Once you plug in the values of fi, you can just substitute and calculate, you know, the values for the derivatives. That example, you can calculate what is df dx, d square f by dx square, and so on, by using these explicit formulae, right? So that's why, I mean, essentially you don't have to solve for anything. You just have to plug in the value and calculate it at one I location, and then you move on to the next I plus 1, you calculate it, or I plus 2, and so on. So that's why these are called explicit finite difference formulae. Now, how do we go about parallelizing them? Let us say we have a 1D domain, okay, and then we have several points. We have a domain length of L, and we have a certain grid point 0, 1, 2 all the way to n. Okay, let us say we know the function form in an analytical way. Okay, so using an analytical function, let us say f of x equals sin x by x cube or something. So we already know the function. Then if you have to calculate the derivative of this function, of course you can always calculate using analytically, but then the idea is when you don't know this function analytically, let's say if you're getting it in your simulation, then you would have basically f of 0, f1 all the way to fn. Then how would you use these values to calculate the derivative? That is basically using the finite difference formula. Then, I mean, all you have to do is you basically have a loop that is for I equal to 0, I less than n or less than or equal to n, I plus plus, right? And then you have df dx of I, you would have one array that would be equal to, let us say if I use the forward difference formula, this would be fi plus 1 minus fi minus 1 divided by, how much is the value we have? Divided by h, isn't it? Or 2h, just h, isn't it? So this is basically h, okay? This is one way to calculate it, or you could calculate even using df dx using the central difference formula, that is f of I plus 1 minus f of I minus 1 divided by 2 times h. Okay, now you could do this. Now only thing what you realize is that, as I said before, you basically near the boundaries, as you go to 0 or n, you end up with accessing the data outside. For example, when you're at 0, you're accessing f I minus 1, that is f of minus 1, and when you're at n, you're accessing the data of f of n plus 1 and so on. So you need to make an exception here. So you need to have a if condition where you would say, if I am at 0, I would use the forward difference formula. Okay, I would use this. And if I am at I equal to n, if I am at I equal to n, then I'm going to use the backward difference formula. Okay, that is one thing you can do. And then if you are in between, that is, say, let's say if you are going from I equal to 1 to I less than n, then you could use this central difference formula, which is second order accurate. Okay, that is fine. Now what about loop carry dependency and or data dependency while calculating these things? Now can we calculate this in parallel, or is there a dependency? Okay, we wish to calculate what is df dx. Df dx depends on f of I plus 1 minus f of I, or it may depend on f of I plus 1 and f of I minus 1 and so on. So as you can see, there is no loop carry dependency or data dependency in terms of writing the values, right? We have, of course, data depends on I plus 1 or I minus 1, but this is only in terms of accessing the variables, right? And fortunately, because we are dealing with a shared memory system, our f is shared between all the threads. As a result, f of any value can be accessed, and it is not changing as we go with between the iterations. But df dx is, of course, can be split between the threads, between the iterations, and df dx doesn't seem to have a loop carry dependency or a data dependency. As a result, we can easily parallelize this, in which we can say f is shared, I is private, and then df dx is also shared, right? So that can be written. That means we can write this as hash pragma OMP parallel for, we could say, default none, okay, and then say shared variables are your f and df dx, and of course the size, that is basically your n, and then your private variables are your I, right? That is your I, and then you have basically for I equal to 0, I less than or equal to n, I plus plus, and then you have your conditions. If at the beginning use something, else if at the end use something else, you would do basically df dx of I equal to f of I plus 1 minus f of I minus 1 divided by 2 times h is what you would do, right? That's your basically your parallelization for spatial derivatives. Okay. Okay, now what about of course, we always don't work with 1D problems. Okay, we do not many times we are interested in solving a problem in 1D. We most likely will be working with 2D or 3D problems, and working with 2D and 3D problems is much more convenient to parallelize than the 1D in some sense. Okay, we will come to that later in the future examples. So what we mean by 2D and 3D is basically you have a grid. Okay, let me draw it here. So basically we have a grid, not progressing. Okay, so basically we have a grid, and then we have to calculate the derivatives. That means we have a j loop, we have an I loop as well as a j loop, right? Then when we are calculating derivatives in, let's say, in one particular direction, then we actually don't need to, we could actually do it for different j, that is also possible. Instead of doing it for parallelizing the I itself, we can even parallelize the j, and similarly we can also parallelize the I loop when we are calculating the derivative for j. In that sense, this can be even applied for 2D and 3D in a straightforward way. Okay, so that is very simple. So extension to 2D and 3D are rather straightforward because there is no data dependency, because I calculation of derivative in one particular direction only depends on I plus 1 and I minus 1 and not on the other values. Okay. But if you end up with a particular derivative, let's say a second order derivative, which is maybe like d square f by dx dy or something, which would require I plus 1, j plus 1, I minus 1, j minus, and so on, then you have to see if that is possible or not. Then if you try to do it in both ways, I think it is even possible for that as well. Okay, if you have cross derivatives as well, it is possible. All right, so that is being said. Then we kind of finish the discussion on the explicit finite differences. Let us look at the final thing, that is implicit finite differences. So the fourth one is implicit finite differences, okay, or implicit spatial discretization or spatial derivative. So this is implicit spatial derivatives. All right, now what do we mean by implicit spatial derivatives? That means we have, in addition to the schemes that we have studied before, which are basically the explicit, first derivative, which is basically forward difference, if it's a forward difference scheme, FDS, backward difference scheme, backward BDS, central difference scheme, that is the central scheme. All these things were explicit because you just have to plug in the value of f of I or f of the function values, and then calculate what is the derivative at any point. Sometimes these schemes are not enough. Sometimes we have essentially another class of schemes which are called implicit schemes. They have higher accuracy, higher order accuracy, even on a small stencil. Okay, so the stencil is what we mean by, for example, if we have a scheme, what we have seen is that the dependency on I plus 2, I minus 2 as I plus minus 1 also is there for f if the scheme was derived to be fourth order accurate. Now we could construct a scheme which only depends on fi plus 1 or minus 1 values and still be fourth order accurate by not incorporating the value of fi plus or minus 2, rather by incorporating the function values and the derivative values at the neighboring points as well to calculate the derivative at I. Okay, so these schemes which are higher order in accuracy with a kind of a compact stencil are known as compact schemes, or first proposed by Pade. These are called Pade schemes. Okay, so these schemes, essentially the calculation of the derivative at a particular point not only depends on the function value at fi plus 1, fi minus 1, it also depends on the derivative value at the neighboring point, that is fi plus 1 and fi minus 1. Okay, so that means we basically have a connection or a link to calculate fi prime also goes all the way to fi plus 1 and fi minus 1. Okay, that means these are not independent, rather they are connected. That means if you were to calculate what is f prime at 1, you would get an equation that connects f prime at 1 to f prime at 0 and f prime at 2, in addition to f0, f1 and f2. And similarly, if you want to calculate what is f prime 2, you would get a relation which goes f prime 1, f prime 3, and you also get f1, f2, f3. Okay, that means you basically have an implicit nature in which the derivative cannot be calculated independently like in an explicit way. Okay, it has to go through some kind of implicit nature because they are all linked. So when you express such an implicit derivative, you will get all the derivatives at all the points. Okay, that is all the way 0, 1, 2 all the way to n in all at a time. Okay, that means you have to you will end up solving a system of linear equations to obtain the solution for f prime. Okay, so which was absent in the context of explicit finite difference methods. Okay, now these are very well sought after schemes, the Pade schemes or the compact schemes. If you look at any of the direct numerical simulations in fluid mechanics or in combustion, or the large eddy simulations and things like that, the compact schemes or Pade schemes are very very well used because they provide a higher order accuracy and also better spectral resolution. That means they can capture the oscillations in the functions even at low resolutions. Okay, so that's why these are kind of well sought after and used. Okay, so one such pattern scheme is what I kind of provide here as an example. So in which for, let's say, if you go back to the original case, you have 0, 1, 2 all the way to n. So if I consider the interior points, that is going from 1 to n minus 1, so for I ranging from, it's not 0, 1, 2, 3 all the way to n minus 1, the derivative fi prime using pattern scheme can be written like this. That means this is basically your fi minus 1 prime plus 4 fi prime plus fi plus 1 prime equals 3 upon h into f prime of I plus 1 minus f prime of I minus 1 plus order h to the 4. As you can see, this is a fourth order accurate scheme which uses, the stencil is so compact, it only uses I plus 1 and I minus 1, and it also uses the derivatives at that function values to make up for the, basically the function values at I plus 2 and I minus 2. Okay, all right, then as you can see, we have excluded the neighboring points here, the boundary points for 0 and n, for which you have special formulae which are basically f0 prime plus 2 f1 prime equals 1 by h minus 5 over 2 f0 plus 2 f1 plus half f2, and then for point n you have fn prime plus 2 fn minus 1 prime equals 1 over h, you have 5 by 2 fn minus 2 fn minus 1 minus 2 fn minus 2. Okay, so these are the formulae. Now how did we get this here? How did we get these schemes? So we did not discuss that, but what you basically have to do is you basically have to write your equation such that, let's say, if you have fi prime plus a times fi minus 1 prime plus b times fi minus 2 prime and all the way, and then you have to kind of maximize this for the highest order possible by cancelling all the lower order terms and expanding these using Taylor series. Okay, so there is a particular process in which you can do that and then obtain these finite equations. Okay, we are not going into the details of construction of these schemes, rather we are more interested in, if this scheme is given to us, how would we go about parallelizing it. Okay, now as you can see, we basically obtained a system of linear equations. Okay, because our unknown is, let's say our unknowns are f0 prime, f1 prime, and all the way to fn minus 1 prime and fn prime. Okay, now for that we basically got a system of linear equations. Now if I were to arrange all this system in a matrix form, then what you basically have is you would get 1, 2 coming from this and this coefficients, and then you would have 0 all the way to 0. Okay, then you have, for the interior points, you would have 1, 4, 1. Okay, 1, 4, 1, and that 1, 4, 1 will keep shifting depending on values you would have, and then you would get basically 1, 4, 1 at the other boundary, then you get 0, 2, 1, and these are all zeros. Okay, so and then you would have this multiplying by f0 prime, f1 prime, f2 prime, fn minus 1 prime, fn prime. On the right hand side you would have values coming from here. Okay, this is basically minus 5 by 2 f0 plus 2 f1 plus 1 half f2, and then here you have I equals 1, so this is f2 prime minus f0 prime times 3, so this is 3 times f2 prime minus f0 prime, 3 times f3 prime minus f1 prime, and so on, 3 times fn fn prime. Is it prime? Oh, it's just, yeah, it is prime. Yeah, okay. Let me check that. Okay, and then we have at the bottom we have 5 by 2 times that's not a prime, that's just the regular value, right? That's just the, there is no prime here, it's just the fi plus 1 minus fi minus 1, that's all. Okay, because the prime is already gone to the left hand side. All right, so and then we have so no primes here. Okay, and then you have fn minus 1, and the last one would be basically your 5 by 2 fn minus 2 fn minus 1 minus 1 by 2 fn minus 2. Okay, so basically we have some right hand side vector b, and then this is the x, that is the unknown, right, and this is the coefficient matrix. Now what you observe here is that the coefficient matrix that we get is basically banded, right? There are only there are three diagonals. You have the main diagonal, and you have the sub-diagonal and the super-diagonal, and everything else is basically are zeros. These are all zeros, and these are all zeros. So we end up with a we end up with a tri-diagonal system or a matrix in which only the main diagonal and the one sub and super diagonals have non-zero elements, okay, and everything else is zero. Okay, so there are special methods available to solve this, but it turns out all those special, the special method that we have is not going to be of very much use when you try to parallelize this, because you have a dependency of fi plus 1 and fi minus 1 to calculate fi prime, right? That you can clearly see here. That means you basically have a data or a loop carry dependency, right, in the calculations. In the formulation system itself we have, which is very much evident when you write the matrix. So as a result, this is not very straightforward to parallelize, or in fact we will see that it is not possible to parallelize this using OpenMP or or any other method. But nonetheless, we will try to see how to formulate and solve this particular system using a special method, and kind of comment on how would we go about this thing. Okay, so we will do that in the next lecture. Okay, I'm going to stop here for now. We'll pick up from here in terms of parallelizing the implicit finite differences in the next lecture. Okay, thank you. Talk to you in the next lecture.